Today I want to share with you some of, should I click continue? Yeah.
Yeah.
So I want to share with you some of my projects in discrete time quantum walks. So let me start by describing a classical random walk on the past. Okay, so let's say we have a random walker here and place him in the middle vertex 2. So this is his initial position. And now he's gonna flip a coin. If it's side up, then he goes left to vertex 1. And if it's side down, then it goes to the right. Okay, so let's say the coin is a fair coin, so there is no preference going left or right. So after one step, you are gonna see this worker at this position with 50% chance, or this position with 50% chance, right? Now he's gonna move again, flip a coin, and you will see him here and here, where he at vertex 1 when t equals 1. Okay, and you could also find him here or here, where he at this vertex. Okay, so after you multiply and sum up the probabilities, you will see one quarter of probability when the worker is here, and 50% chance when he's here, and 1/4 here as well. And this procedure continues. Okay, so we can put all these probabilities under each vertex and view it as a vector or probability distribution. So in general, the state of a random walk is given by such a probability distribution over the vertex set. So let me write down something over the vertex set. By the way, in this talk, I will use X to denote the graph. And how does the random walk evolve? Well, it's gonna be determined by a matrix called a transition matrix. Okay, so if the state at time t is equal to xt, then the next step we are gonna have xt plus 1 equals some transition matrix times xt. Okay, and because this guy must map a probability distribution to another probability distribution, we must have a stochastic matrix here. Okay, and because it also respects the recency matrix of the graph, so this transition matrix is a stochastic weighting of the recency matrix of the graph. Okay, and such a weighting exists for every graph because we can just divide the recency matrix by the degree of each vertex. So for each row, let's say this one, you divide it by 1, and this guy has degree 2, so you just divide the whole row of the recency matrix by 2, and so on. So that procedure generalizes. Now, how do we describe a quantum walk on such a graph? So here, from the axioms of quantum mechanics, we know two things. First, every step must be a unit vector. Okay? And second, the allowed operation in a quantum system must be unitary. Okay, so a unitary matrix maps a unit vector to another unit vector. That's quite natural. So intuitively, we want to let the states be unit vector indexed by the vertices, just like before. So let's say this is in C to the arcs. Oh, sorry, not yet. C to the vertices of the graph. Okay, so for example, I could start with this initial state, 0, 0, 1, 0, 0. That is a valid unit vector. Now the next step, we are gonna go to another unit vector supported only by the neighbors of 2. So you could have something like 0, let's say 1 over root 2 here, 0, 1 over root 2, 0. Okay, and we want this to be true no matter where we start in the graph. So that means the transition matrix must be a unitary weighting of the recency matrix of the graph. Okay. Now here comes the problem. There is no such weighting for the path of 5 vertices. And the problem is caused by these 2 columns. Okay, you can see they have exactly one common support, which is this index by vertex 2. So no matter how you weigh the entries of this matrix, you can never make these two columns orthogonal. So in general, if the graph has two vertices that share exactly one neighbor, then you cannot find a unitary weighting of the adjacency matrix. That means this naive approach doesn't work. So how should we get around that problem? Well, the way to fix it is to enlarge the state space. Okay. Now, instead of looking at vectors indexed by the vertices, we look at those indexed by the arcs of the graph. Okay, so an arc is just a directed edge. And given a directed graph, we can replace every edge by two arcs with opposite directions. And in this graph, you will see every state is a unit vector of length 8 because there are 8 arcs. Okay, and now suppose my initial state is this 0, 0, 1, 0. Let me erase the others. 0, 0, 0, 0. Okay. Then the next step of the quantum work is to move to an adjacent arc or many adjacent arcs at the same time. Okay, so how should we describe that procedure? Well, first of all, we can define the adjacency of arcs in this way. If you take two arcs AB and CD, okay, we say an arc AB is adjacent to CD if the head of the arc B head is equal to the tail of the next arc C. So for example, 0, 1 is adjacent to 1, 2. However, this is not a symmetric relation because in general, the head of the second arc is not equal to the tail of the first arc. Okay, so that's different from the adjacency of the vertices. Now, given this definition, we can construct a so-called lie digraph from the original graph. Basically, all the vertices here are the arcs of the original graph. So there are 8 of them. Okay, and the adjacency of these vertices is exactly the adjacency of the arcs they represent. So this is a mixed graph. You will see one directions between two vertices, or sometimes you will see a diagonal between two vertices that represent opposite arcs of the original graph. Okay, now we can describe the transition matrix. It has to be a unitary weighting of the lie digraph. So now I will replace this by A of LD X. And this is no longer true, so I'm gonna close it up. Okay, so for example, for the path of 5 vertices, this is a unitary weighting of the lie digraph. You can see that every 2 rows you pick are orthogonal to each other. Moreover, if you look at each row, okay, it's only supported by a few arcs, and these arcs, their tails are exactly the head of the row index, and that's why this is a unitary weighting of the adjacency matrix of the lie digraph. So that's sort of a combinatorial interpretation of a quantum walk. But when people first studied quantum walks, they didn't think of it in this way. They didn't start by looking at a lie digraph and throwing some ways to make it unitary. Instead, they give another description, which is also imperative. So let me go to the next page. So if you think about a classical random walk, what is he doing? Well, he's standing at the middle vertex and then flip a coin and then shift according to the coin's direction. Okay, and then flip the coin again, and maybe the coins tell him to go right again. And then flip the coin a third time, he may go back. So that is 2 steps in one iteration, a coin flip and a shift. Now, in terms of a quantum walk, we can also describe every step as a coin flip and a shift. Now, let's suppose the initial state is this arc. Okay, so we have zeros everywhere else, but one here. Then we can think of these arcs as two pieces of information. First, the tail of the arc is where the worker is standing on, okay? And the direction of the arc tells him where he's gonna move in the next step. Now, he's gonna flip a coin to determine if he still wants to move in this direction, or maybe he should change his mind and move backwards towards one. So that is done by a unitary matrix that acts locally at each vertex. Okay. And this is so this is a general form of a coin matrix, but I've also included a specific example here. So you can think of it as a block diagonal matrix where each block is indexed by the outgoing arcs of the same vertex. So for example, because we are starting with vertex 2, then effectively we are only applying this block to a 0, 1 vector. Okay, and after he tosses a coin, he's gonna move from the arc 2, 3 to a linear combination of two arcs, 2, 1 and 2, 3. And the coefficient of that state is determined by these two. So that is the state after coin flip. Okay. So there are some common coins we can assign. Yes.
I have a question. So you are having a unitary matrix C on this page, right?
Yes.
And you had another unitary matrix on the last page. So are those two related or not? I'm a bit confused.
Yes, they are related. So this is gonna be my U, and I'm gonna describe my U as a product of two matrices.
Ah, I see.
Yes.
Thank
So
you.
no problem. So the point here is we want to construct unitary matrices that are sparse, and they usually come from two sparse unitary matrices. One of them is called the coin flip, and the other is a permutation matrix.
Ah, okay. You can express U as a product of S and C. Okay,
yes.
Got that. Thank you.
Okay. Yep. So so in this C matrix, because as you pointed out, because C has to be unitary, every block must also be a unitary matrix. So some common choices for them are the Fourier matrix of order of size D by D, or a Grover coin, which I will mention later, but this comes from the famous quantum algorithm called Grover's search algorithm. Okay. So here we have Fourier matrix of size 2 by 2, so it's actually a Hadamard coin. Now, what should we do after a coin flip? Now we need to push the quantum walk forward, right? Just like in the classic random walk, after you flip a coin, you need to go forward. And that is done by a permutation matrix of the arcs. So basically, I want to move this arc to another arc whose tail is a neighbor of this. Okay, so for example, I can go here, or I can go here, but it must be a permutation. So this S matrix is a permutation matrix that maps each arc to one of its adjacent arcs. And the easiest way to do this is to just reverse arc. So I can go from here to the reverse direction, or here to the reverse direction. And if you express that arc in block diagonal form, you will see something like this. Okay, so so now we can also partition the arcs, but in a different way. Basically, every block is indexed by the two directions of one edge. And we just do a 2 by 2 permutation of these two arcs. Okay, so after the shift matrix, we go from a linear combination of these two directions to the same linear combination of the incoming arcs of 2. So that is what the shift matrix is doing. Now, combining these two together, the transition matrix is a product of S times C. And then you can do this multiplication manually and see that unitary matrix is exactly what we had before on the previous page.
Actually, there's a comment in chat if you would like to check that.
Okay, let me see. So U is a product of two matrices, each of which is yes, exactly. Each of them is a direct sum of small dimensional matrices. And the nice thing about this path is that you can partition them without changing the labeling. But in general, if you express C as a block diagonal matrix, then S is block diagonal with respect to a different ordering of the arcs. Okay, so that is one step of a quantum walk. Let me show you more steps. So here, if I start with this arc, okay, then in the next step, I will go to a linear combination of the incoming arcs because we are looking at the rows, sorry, the columns of the adjacency matrix of line diagram, not the rows. So it kind of flips the incoming and outgoing arcs. But now the next step, we are going to move from this arc to two incoming arcs of one, okay? And we will move from this arc to two incoming arcs of three, and this procedure continues. Now, in the physical lab, we cannot observe these numbers, but what we can observe is their squared modulus. These are called probabilities. So if you do a measurement, okay, you will find the worker at a particular arc, let's say 0, 1, with 0.5 squared probability. So I can record all these numbers and turn them into some shades. So here is the evolution. The worker starts with this, so you will see a very dark circle here. And then after one step, you're going to find him in both arcs with equal chance. And then you kind of spread out to these 4 arcs. And then later you will see he goes back to this and maybe this arc with a very high probability. And then he moves to 3, 2. So that is the probability distribution over the arcs at each step. Okay, now our original question is, what about the probability on each vertex? Well, that is simple. You just do a measurement at a particular time, let's say t equals 5, and then you can just take the sum over all the outgoing arcs. So the probability is here at vertex 1 is equal to this guy plus this guy. And I'm going to show you an animation. So still starting from 0, but you can see he kind of wanders to the left first and then slowly moves to the right. Okay. So this is very different from a classical random walk because in classical walk, you will see it moves to the left or right with symmetry, and the probability over all the vertices gets more and more uniform as it increases, but it doesn't happen in the quantum walk. So what are some interesting phenomena that we want to look at? Well, first of all, for this graph, you will see that in a classical random walk, it mixes very quickly. So all the numbers get closer and closer to each other, but in a quantum walk, it's different. So here at t equals 6, you will find worker on this vertex with certainty if we started with this vertex. So this is a phenomenon called perfect state transfer. So we are starting with all the outgoing arcs of the same vertex. Okay. And after 6 steps, you will find the worker on all the outgoing arcs of the opposite vertex.
Here's a question. May I ask why the behavior of classical work and quantum work are so different? Is there any reason for that?
So basically, there are two different procedures. The classical one is a stochastic process.
Okay.
So let's say I want to go from this to this, right? And the more paths there are, the higher chance I will arrive at that position. But in the quantum walk, the transition is governed by a unitary matrix. So instead of putting probabilities on the arcs, you put some complex numbers. So you can view them as complex probabilities, which will cancel out.
I see.
Yeah. So
okay.
I don't know if that's explains.
Okay, thank you. I
Why?
kind of got the idea. Yeah,
Okay.
thanks.
Yep. Now let's look at the bipartite graph. So both classical and quantum walk will alternate between the odd and even distances. But again, you can see this probability is the same in each class. But here, well, if you measure the quantum walker, you're going to find him at this vertex with very high probability. Although it doesn't equal 1, but for any epsilon, you can find a time so that this probability is epsilon close to 1. So that is called a pretty good state transfer. I'm going to write, we'll stop here. For every epsilon greater than 0, the probability at a vertex is greater than 1 minus r for some time t. So that means you can go from one point to another point with high probability. Now the third thing, oh, I'm missing some. Let me fix it very quickly. Anyway, so you please imagine there are two other dots here, but I'm just saying the limiting distribution of a classical random walk is uniform everywhere on the vertex, but the limiting distribution of a quantum walk is not necessarily true. So for the global coin, you are gonna see higher probabilities on these two vertices if you start with here. But for some other coin, you may still have these uniform average mixing properties. So I will talk about this later. This is actually not the limit of the state, but an average limit, a Sassaro sum of the probabilities. Okay. So how should we make use of these properties? Well, there are many applications in the algorithms. For example, the Grover search, which offers a quadratic speed up over the classical algorithm, is a quantum walk on the complete graph with loops. And the other algorithm, due to unbindings on element distinctness problem, is also a quantum walk on the Johnson graph. Okay. Now in 2004, Ansagli proposed a way to quantize any algorithm that's based on a Markov chain, and then you can compare the heating time for the classical random walk and the quantum walk and realize there are some differences. For example, Kemp showed that on the hypercube, the quantum walk can heat exponentially faster than the classical random walk. So that is some phenomenon we can use if there's quantum computers. But for us, we are more interested in the relation between a transition matrix of a quantum walk to the properties of the graph, because we are working in algebraic graph theory, right? So let me first explain how we can express some quantities of the quantum walk using the eigenvalues of the transition matrix. So here, because U is unitary, every eigenvalue lies on the unit circle. So I can write the eigenvalue as e to the I theta r for some real angle r. So this is my eigenvalue of U. Okay. And for each such eigenvalue, I can let Fr be the orthogonal projection onto the eigenspace. Okay, so there are some properties about Fr. First of all, it's a Hermitian matrix and it's an idempotent. And for distinct eigenvalues, we know their eigenspaces are orthogonal to each other. So we have Fr times Fs is equal to 0 for any r not equal to s. Okay. And once we have this spectral decomposition, we can compute any functions in the matrix U by computing the same function in the eigenvalues. So for example, to evaluate the transition matrix raised to t's power, we just raise the eigenvalues to t's power. And that is much easier to do computationally. Now, The state at step t given initial state x naught can also be expressed as a sum of e to the it theta r times each eigen projection applied to x naught. Now, how about the probabilities at step t? Well, it's coming from the squared modulus of these long vectors. So, so those are represented by this Schur or element-wise product of this vector and its complex conjugate. So you can also expand that using the eigenvalues and eigenprojections of U. Now, because U is a unitary matrix, this guy does not converge as t goes to infinity because U kind of preserves the difference between two consecutive states. Okay? But we can take the average of that probability distribution over a period of time. And when t goes to infinity, this guy does converge to a limit. And that limit depends only on the eigenprojections. Finally, if x naught is only supported by one arc, then we are talking about a column of FR Schur product with the same column bar. Right? So we can record all that numbers into this limit, which is really just the sum of FR Schur FR bar. So it's a very simple expression, and you don't even need to consider anything quantum. It's just coming completely from the transition matrix eigenprojections. In the end, I also want to mention something else. So you can even take the logarithm of U, which is congruent to I times the angle theta r times fr modulo 2 pi. So there are many different choices for the logarithm. And I will mention why we are interested in this later. So again, we want to know the relation between the quantum properties of the walk and properties of the graph. However, in general, this is not very clear because U is a product of two matrices which do not commute. Okay, so U lies in a non-commutative algebra, which is not the adjacency matrix algebra of the graph. So a better question to ask here is for which permutation matrix S and for which coin C is the property of U related to some graph structure. Okay, so to answer that question, I'm gonna restrict it to a special case where R is just the arc reversal matrix. So it maps arc AB to the arc DA, and C has order 2. So it represents a reflection about a subspace. Okay, now to diagonalize the matrix U is the same as to decompose the state space, right, into one-dimensional U-invariant subspaces. So we can do that in 2 steps. First, I'm gonna decompose this into RC invariant subspaces. Let's call them W1, W2, and so on. And next, I can diagonalize U inside each of these invariant subspaces. Now, there's a very nice theorem from the representation theorem of dihedral group saying that if R and C are both involution, then we can make these W's 1 or 2 dimensional. So it's not too bad. In the end, the worst thing we need to do is to diagonalize a 2x2 matrix to find the eigenvectors of U.
Yeah,
so that is the
one
idea.
question. So maybe I have missed something. So could you give me an example of the matrix R, the arc reversal matrix?
Yes. Okay. So the example is here. And these are all the arcs, same arcs in the same order.
That one.
Yeah.
Okay.
And for each edge, you have 2 directions. And the arc reversal is just swapping these 2 directions.
Oh, I see. Thanks.
Right. So in this talk, I'm going to consider only the arc reversal matrix as the shift matrix, but the coin matrix has many choices. The only requirement is it has order 2. Okay, given that, we can decompose the state space into 1 or 2 dimensional invariant subspace under RNC. Okay, now I will omit the details about how to diagonalize U here, but just give you a correspondence between a smaller matrix and which is n r n star and the matrix U here. So because C is a reflection, okay, let me write down this is a reflection about a subspace, we can always write it as twice the projection minus the identity. So Q here denotes a projection matrix about the same subspace. We also know that every projection is a grand matrix, so we can find a matrix N whose rows are also normal, so that this identity holds. Rows also normal. Okay. So once we have this matrix, we can conjugate the arc reversal matrix R by N. And most of the eigenvalues of U are coming from eigenvalues of this guy in a very simple way. So by interlacing, we know the eigenvalue of this smaller matrix lies between the eigenvalues of the reflection matrix, which is 1 and -1. So each of the eigenvalue of N, R, N star will give rise to 1 or 2 eigenvalues of U. So if lambda is equal to 1 or -1, then they contribute partly to the real eigenvalues of U. Okay, and if lambda lies strictly between -1 and 1, then they contribute to a pair of complex eigenvalues of U whose real part is equal to lambda. So in a word, every eigenvalue determines the real part of some eigenvalue of U, and you can find the imaginary part very easily. And here's how you leave the eigenvectors to eigenvectors of U. These two are corresponds to the one-dimensional invariant subspace, and the span of these two vectors give you the two-dimensional invariant subspace of RNC.
So basically, if you know the eigenvalues of N, R, N star, you know the eigenvalue of U.
Yes, that's true.
Okay.
Yes. Okay, so now let me specialize to a famous coin, Grover coin, and see what this means, because that pretty much determines the spectrum of U. So let me describe the Grover coin first. It's a linear combination of the identity matrix and the all-ones matrix. So you have a constant diagonal and constant off-diagonal. So what does this mean in terms of the worker? Well, if the worker is standing on an arc from 0 to 1, let's say, then after he tosses the coin, he's gonna be everywhere on every outgoing arcs of the same vertex, but with coefficient 2 over d minus 1 at the original arc and 2 over d everywhere else. Here d is the degree of the graph. And I'm gonna assume the graph is regular. Okay, just to make life easier. So the Grover coin is quite symmetric. It doesn't care which arc you move to, as long as you leave the original arc, it always assigns 2 over d to that arc. And if you stay in the original arc, it assigns 2 over d minus 1. Now, this coin matrix is a reflection, and we can find the projection onto the column space in this way. So it's really a reflection about vectors that are constant on the outgoing arcs of the same vertex, or the column space of the arc tail incidence matrix. So dt records the incidence structure of the vertices and the arcs. Okay, and a vertex is incident to all the outgoing arcs of that vertex. Now this dt is our n in this table. So let's try to understand what dt r times dt star means. Well, R is the matrix that swaps tail with the arc, right? So if you multiply R by dt transpose, then we get another incidence matrix between the head and the arc. I'm gonna call it dH. This is equal to the head arc incidence matrix. Now it's an exercise to check that dt times dH transpose is exactly the adjacency matrix of the graph. So what are we saying here? By this table, we find that every eigenvalue of the underlying graph determines the real part of the eigenvalues of U. And that is something quite surprising because we constructed the transition matrix from something that's kind of arbitrary. It doesn't depend on the adjacency matrix of graph, and U is not in the adjacency algebra, but somehow its spectrum is still determined by the eigenvalue of the adjacency matrix. And that is pretty cool, I think. And to be more precise, for deregular graph, the largest eigenvalue of A is equal to D. So it gives rise to the eigenprojection onto the one eigenspace. And minus D is eigenvalue if and only if the graph is bipartite, and it will give us the other real eigenvalue of U. And all the other eigenvalues of A is going to give us a pair of eigenvalues. And you can also leave the eigenprojections using this formula. Okay, so with that tool, we can characterize many phenomena we just discussed. One of them is the perfect state transfer. So it says that PST, or perfect state transfer, occurs between two vertices if and only if these three conditions hold. First, the vertices must be what we call strongly co-spectral. That is, if you look at the projection of the characteristic vectors of the two vertices for each eigenspace of A, then they are just plus minus one of each other. So this is condition that strengthens co-spectral. It implies the co-spectrality of two vertices plus something we call parallel. So I'm not sure if you are familiar with this concept, but basically two vertices are co-spectral if the characteristic polynomial of the graph with A deleted is equal to the characteristic polynomial of the other vertex deleted graph. And there are many combinatorial interpretation of this. For example, for co-spectral vertices, the closed work at vertex A with length L is equal to the number of closed work at vertex B with the same length. So if two vertices do not have this property, then you cannot have perfect state transfer between them. Now, in addition to this strong co-spectrality, we also want the eigenvalues to satisfy some number theoretic condition. So these three properties give us a very specific goal to look for when we study perfect state transfer. And using that, we can construct an infinite family, which is a circular graph over Z2n with a connection set of this form.
Okay, just to be clear, so by saying perfect state transfer among two vertices, you mean with probability 1, you can go from one to the other. And for the pretty good state transfer, that probability is arbitrarily close to 1, right?
Yes, that's exactly
true. Okay,
yes.
Thank you for clarification.
Sure. Right, so why do we study pretty good state transfer? It's because perfect state transfer is really rare. Okay, so if you look at this condition, it says something very strong algebraically about the eigenvalues. And most of the graphs do not satisfy this condition. So we look at the relaxation. Can we have pretty good state transfer from a vertex to another vertex to arbitrary precision? So for this, we also have a characterization, and this is a joint work with my current supervisor, Zhan. So again, we want the two vertices to be strongly co-spectral. But now, instead of having an exact description of the eigenvalues, we want them to satisfy some conditions. So the details here are not important. The highlight is that theta r is coming from the eigenvalues of the graph, and we want to measure how linearly independent they are over the rational numbers. And the more linearly independent, then the more likely we're going to have pretty good state transfer. And this characterization is coming from a very old theorem due to Kronecker. So if you're interested, you can look that up. Okay, but now I'm going to move to a third property, that is the logarithm of u. So let me digress a little bit to talk about the continuous time quantum walk. So given a graph X with adjacency matrix A, a continuous quantum walk is also determined by a transition matrix, but that matrix is much friendly to us. It's just the exponential of I times t, which denotes the time, times the adjacency matrix. So for any for any time t, you just evaluate this matrix, and the entries or squared modulus of the entries will tell you the probability that the walker moves from one vertex to another vertex. Okay, but in general, every unitary matrix can be written as I times exponential of I times some Hermitian matrix. So we can say that every U is a transition matrix of a continuous walk on some graph. The only problem is H is usually very dense. So it represents a weighted complete graph in general, right? So the question is, for which U can we find H so that the underlying graph is sparse and nice and related to the original graph? Now, we have the spectral decomposition of the algorithms and work with global coins, right? And using those spectral correspondence, we can show that for every invertible distance regular graph, or even graphs lying in the association scheme, we have a nice relation between the discrete walk and a bunch of continuous walks. So this is saying when you take the square of U, okay, then it factors into a bunch of transition matrices of this form here. And moreover, each of these Hermitian matrix H here is the skew adjacency matrix of the J's distance digraph of Lie digraph. So there's a lot of combinatorial relations between the discrete work on the original graph and the continuous work on these directed graphs. So for example, if the graph is complete graph, then a discrete time quantum walk on a graph is equivalent to a continuous quantum walk on the Lie digraph. How much time do I have? I'm almost running out of time, right? Okay.
Oh, I'm muted. I think you have 5 to 10 more minutes.
Okay, 5 to 10 more minutes. Okay,
yeah.
So let me quickly mention 2 more phenomena. The first one is in the limiting distribution. Okay, we are asking for which graph can the quantum walk be uniform over all the vertices. Okay, so this is not a new problem. Actually, back in 2001, Aharonov and the others asked these questions for a different model. That is, can we find a transition matrix so that no matter where you start, like regardless of initial state, the limiting distribution is always uniform over the vertices. Of course, in that paper, they study a different model, and they give a sufficient condition, that is, when U has simple eigenvalues, then we have this property. Now, for our model, we don't have something that strong, but we can give a weaker characterization in terms of the eigenvalues of A. That is, if the graph has simple eigenvalues, Okay, then for any initial state that's constant on the outgoing arcs, for example, you assign the same numbers to the outgoing arcs of 3 and the same numbers to the outgoing arcs of 1, then as long as your initial state is of this form, then the probability distribution is always uniform over the vertices. Now the problem here is there's no such graph, because we are assuming the graph is KD over the billion group, and the only vertex transitive graph with simple eigenvalues is the graph on two vertices. Okay, so that motivates us to look at a different coin, which I will call a weighted Grover coin. It's very similar to the Grover coin, but instead of looking at the incidence matrix, 0, 1 incidence matrix, I put some weights to these entries. Okay, and these numbers can be any complex numbers, but I will insist they lie on the unit circle. So then we can construct C as a weighted Grover coin. And as before, the spectrum of U is determined by this smaller matrix. And it turns out that it's not the adjacency matrix of graph, but the Hermitian adjacency matrix of maybe a mixed graph. And those are the entries of this Hermitian matrix. Now, if these Ws are roots of unity, then I can replace each of the entry by a permutation matrix of appropriate size, and we can blow this Hermitian matrix up to a large 0, 1 matrix, which is the adjacency matrix of a cover of the graph. Okay, so that is one connection between quantum walk and covers. And in addition, if the graph is KD over the billion group, then we can say something more. Okay. So here's the same result we borrowed from the previous slides. If the weights on the arc, okay, only depends on the connection set. So for each element in the connection set, you assign a weight, and for every arc induced by the connection set element, you assign the same weight. Then the Hermitian matrix having simple eigenvalues implies that the limiting distribution is uniform regardless of any initial state lying in this column space. Okay, so now we have a better chance for achieving that distribution. For example, this is a circulant graph on 6 vertices, and it has connection set 1, 2, 4, and 5. Okay, so we can assign 4 different fifth roots of unity to the arcs. So this is the arc induced by 1, and we are going to assign the first fifth root of unity. And for this arc induced by 2, we assign something different, and similarly for these 2. Then you can check that the probability distribution is indeed uniform, no matter which vertex you start with. And another way to do this is to divide the connection set into 2 parts. So the elements that do not exceed half of the number of vertices and the elements that does exceed that. And then we can assign the 12 roots of unity to the first set. Okay, so these 3 arcs receives this number, and we can assign the conjugate of the 12 roots of unity to the rest of the connection set elements. Now it turns out that if you do that, then the H matrix is actually something that has been studied by Boyamoha last year. And for this particular graph, this Hermitian matrix does have simple eigenvalues. So, well, by choosing a different coin, we sort of engineer uniform average mixing on these graphs. Okay, so perhaps a future direction in this area is to see which of these Hermitian matrices will have simple eigenvalues, and that will tell us uniform average mixing matrix. And the other question related to pretty good state transfer is when we compute the eigenvalues of this Hermitian matrix and do this sort of a transformation, then how linearly dependent are these numbers? If we understand this, then we understand pretty good state transfer with respect to this weighted coin. Okay, so finally, I want to quickly mention a third choice of a coin circular coins. And this is related to an orientable embedding of a graph. Okay, so here K is a circular matrix. Now, if every K is a cyclic permutation matrix, then C defines a rotation system because every block assigns a cyclic permutation of the outgoing arcs of the graph of the vertex, okay? Or a cyclic permutation of the neighbors. So C defines a rotation system. And you can show that the orbits of U, which is now a permutation matrix, is exactly the faces of an orientable embedding. Now, in this very special type of quantum walk, the choice of the average mixing matrix has a very nice interpretation. So let me explain that very quickly. Because this is the average mixing matrix. Now, because U is a 0-1 permutation matrix, taking the short product does not really affect anything. So I can drop this term, okay? Now, U has finite order. So when we take the average as t goes to infinity, this is really the average over a finite period, which is the order of the permutation matrix U. Now I can take the trace on both sides. Okay. Trace here, and that boils down to the sum of trace of U to the t. But that is really the number of points fixed by an element lying in the cyclic group generated by U. So by Burnside's lemma, this is equal to the number of orbits or the number of faces of the orientable embedding. Okay. So that's what happens when you take a permutation coin. Now, in general, if C is I tensor K for some circular matrix, we will refer to it as a quantum rotation system. And here's example. We have a toroidal embedding of some graph, cubic graph on 18 vertices. And if I assign this coin to every block and look at the average mixing matrix, then you will see that on the diagonal, okay, it has a very high transbeam there. So that measures the laziness of the worker in the long run. And if you take the trace of this matrix, then it somehow measures this laziness, but it does not distinguish which arc you are in. So the question is, for a quantum rotation system, can we say something similar about the trace of the average mixing matrix? And we cannot do that in general. I cannot do that for now, but if the embedding is orientably regular, then I have some partial results. For example, the trace is always rational, no matter what entry you throw into this circular matrix. You can even throw in some complex numbers. And the second fact is that the trace of every mixed matrix is at least this number. So that is something that does not depend on the coin again. It only depends on the irreducible representation of an automorphism group that preserves the orientation. So my question is, what about an upper bound? Because I have done some calculation. It looks like for most circular coins, the trace is always less than the number of faces. So if you can characterize the coins that do not have this property, then I think it will mean a lot to the quantum information community, because it's saying that regardless of the coin you take, okay, the laziness of the worker is determined by the underlying orientable embedding of the graph. Yeah, so that's just a summary of what I have done. I consider the arc reversal works with 3 different coins. The Grover coin is related to the normalized recency matrix, and the logarithm is related to the Ladai graph. And for the weighted Grover coin, everything boils down to a Hermitian recency matrix of a mixed graph, and there's also some relation to the covers. Finally, for a circular coin, we can study the transition matrix from an embedding point of view. So that's all I want to talk about today. Thank you.
Thank you so much. Let's unmute and clap for harmony. Any question or comment? Okay, I have a quick question. So you said that the real part of the eigenvalue of U can be determined by the eigenvalues of a adjacency matrix, right?
Yes.
Yes. How about the complex part, the imaginary part?
Okay, so that result holds for the, let me go back, the Grover coin only. Okay,
Yeah.
and you can see that this guy is a real matrix, right? It's a zero matrix.
Yep.
And by the construction here, C is also a real matrix. So that means the eigenvalues of U must come in conjugate pairs, right?
Okay.
Now, if you know the real part on the unit circle, let's say somewhere here, then there are only two choices for the imaginary part because these eigenvalues must have unit modulus. So both of them will give you eigenvalues for you.
Oh, I see. So you actually determined the exact eigenvalues.
Yes, it's completely determined by the adjacency matrix.
Okay, okay. That's actually quite beautiful because my biggest takeaway of your talk is some, I don't know, elegant and also mysterious connection between the discrete world and the continuous works. Yeah, that's fantastic talk.
Thanks.
Yeah. Any more questions? If not, let's thank Harmony again, and we are about to conclude today's session. Thank you so much.
Thanks.
Yeah, yeah, and see you in the next week. Thank you.